Hello? Smaller class today. Well, I hope we didn't have anyone quit after homework 1. I hope not. We're almost done grading your homework 1. Like I promised, we're going to be lenient with the expectations so that you get to solidify what the expectations are. But as of homework 2, we're just going to implement the policy. So, for example, if there's no PDF submitted for your assignment, it's not going to be graded until the PDF is submitted. And by the time it's submitted, then it's subject to the late submission policy. So make sure you get your PDFs thing sorted out, figured out. Okay, you have plenty of time before the deadline. I would recommend, as you are working on your homework assignment, try it out, okay? Try to export to PDF. If you run into issues, reach out to us. But if you reach out at 11 p.m. before, the midnight deadline, probably we're not going to be able to answer you in due time. So, and do copy me and the TAs on all course-related communications, please, so that we get to answer you between the 3 of us. We're likely to have a shorter time to be able to get to your question, okay? Read the feedback given to you by Nicholas and Brooke. They're working so hard to get to grade your homework and look at them. They're giving you plenty of feedback, and they're consulting with me on individual assignments. So make sure you read the feedback, because that is going to be your one shot to kind of figuring out what the expectation is, okay? I want to finish with the discussion on errors today. This year I'm teaching this topic a little bit differently. I'm spending a little bit more time on it because I eliminated some other elements in the course that are not necessary based on discussions with your former colleagues. So we want to spend a little bit more time on errors and definitely the Taylor series. Last time we introduced the Taylor series. We're going to revisit it again in a few weeks, but we kind of just exposed you to the idea of the Taylor series, that given function values and its derivatives at a point, then you can estimate the function at any other point that is close or within the vicinity of where you know information about the function, okay? That's one form of the Taylor series that we talked about last time. And last time we left off asking you to write the Taylor series of the exponential function, e to the x, in the vicinity of a equal 1. So in other words, if x, what this means, that if the x value here is close to 1, then any truncated value of this expansion is going to be a good approximation. Now, if you write the full series, it's an exact thing. Okay, it's exact. But in practice, we're not going to be able to write the full series, so we're going to truncate at different terms, right? We're going to pick 1, 2, 3, 4 terms, right? And the more terms you add, the better the approximation. Now, I want you to visualize that so that I prove to you that, indeed, around point 1, if x is close, then, you can get away with less terms if you're close to 1, with less terms than the Taylor series. Why do we need less terms? Because it's cheaper to use less terms. And when we go to finite difference methods, it's going to be much easier and much less complicated to deal with less terms than the Taylor series. So we need to be close to the point in question. But we want to also see what happens as you add more terms. So that's going to be our next coding activity. Put your name tags in front of you, please. Your group tags, and get your Jupyter notebooks up and running for our first coding activity, and it is to visualize the Taylor series. Again, I encourage you to work in groups. I see you in the help sessions and the student center working together and collaborating, cooperating, copying, all sorts of that fun stuff. So as long as you're learning something, okay? So have a moment, read the coding activity. I'll read it with you. So for the function, the exponential function e to the x, in the vicinity of a equal 1, which is the Taylor series we just wrote, I want you to plot 1, 2, 3, and 4 terms of the Taylor series expansion of e to the x around a equal 1. In other words, I want you first to plot the first term only of the Taylor series, which is e, which is a constant. It's going to be a straight line. Then I want you to plot 2 terms, which is e plus e times x minus 1. And then 3 terms, and then 4 terms, and then compare to the full function e to the x. We're claiming that the Taylor series is an exact representation of any function, any continuous function, if you take all the terms. But if you take a subset of the terms, it's going to be accurate within the vicinity of the point we chose, in this case 1. So I want you to try that out, okay? So go ahead, let's see what you can come up with. So in terms of when thinking about Python, we did indexing and slicing, we did for loops, while loops. Today is going to be essentially the last piece of the puzzle, which is plotting and creating what we call linear spaces. So if you've done MATLAB, you would plot a function versus x, for example, right? This is what I want from you here to do. I want you to plot all of these functions as a function in terms of x, as x is changing, okay? If you have no idea where to start, that's okay. Has anyone done a lin space in MATLAB, a linear space in MATLAB? Okay, have you done a lin space in Python? Okay. Okay, for those, so it looks like it's a subset of you, so let's do it together. I'll do it with you. All right, so I'm going to create a new notebook. See. All right. So first I want to get my boilerplate in. Eventually what you will do, you'll just copy that from some other notebook, okay? We're going to do import numpy as np, and then import. Today we're going to do plotting. I don't remember if we did plotting together last time. We're going to dig a little bit deeper into plotting, but the classic library for plotting in Python comes from matplotlib. And the syntax to do that is to import matplotlib.pyplot, Python plot, and we typically give that an alias. We call it plt. So you notice we say import library as something. So I'm nicknaming the library. So I don't have to call numpy every time I want to call something from numpy. So I don't have to call matplotlib.pyplot.something every time I call it. Just give it a nickname. I call it plt, essentially short for plot. And we're going to need the math library to do the factorial for the Taylor series, okay? All right, perfect. So I'm going to do this in the just do a brute force approach. Okay, for this. But first, I want to plot the exponential function. Okay, my exponential function is e to the x. I don't have to create a Python routine for that. I can just call numpy.exponential, okay? But I need a set of x values, right? If I want to see the variation of e to the x, which looks like this, you know, just exponentially goes up, I need a set of x values, right? -1, minus 0.95, minus 0.85, etc., right? So I need a way to create those. You can type those in manually, but what if I ask you for 100 values or 500 values? Doesn't make sense to type those in manually. There's a little feature in NumPy that allows you to create a set of equally spaced points, okay, from a start to an end, just like the range function allowed us to do a set of equally spaced integers. You can do the same, but create a set of equally spaced floating point numbers. And that function is called linspace. And it's simply as this, numpy dot linspace. Okay, now if you press Shift Tab, gives you the function signature. Start, stop, and then a bunch of other things that have values in them. Let's worry first about the start and the stop. Start is the starting value of this linear space, and stop is the stop value. So let's try it out. If you're in doubt, print it out. Yes, okay. All right, so let's do from 0 to 1, okay? It created an array starting from 0. Let me zoom out a little bit. 0, 0.204, 0.0204, 0.0408, etc., all the way to 1. One moment. We're getting there. All right. You can do this between any 2 points, -2 and 5, right? So look at that. It starts at -2, ends at 5, and creates equally spaced points in between. Now, Miles asks a good question. Looks like the size of this array is the same, and it's like defaulting to a fixed number of points between the start and the end. That comes in through the third argument over here. Okay? So if you look at the function signature, you see this num over here? That's the number of points you need on this interval. The number of equally spaced points, including the first and last point. Okay? So let's go now, say from 0 to 1. 0 to 1, 100 points. I can type num equal 100. Ah, look at that. Very nice, beautifully equally spaced. Okay, starting from 0 all the way to 1. Okay, 100 points. You can do 200. You can do whatever you want. Okay? That's all you need to create a sequence of numbers that are equally spaced. Now, we're going to need that to create an exponential values for the exponential function and then plot them, right? Okay, so let's call this our x values, okay? And I'm going to go with this assignment, with this, if you look at the slides, I want it to go from -2 to 3. Okay, and I want 100 points, okay? Now, like we learned last time, because this is a numpy array, any numpy function can operate on a numpy array point by point. So if I call the numpy exponential function on these x values, on this linspace, it's going to apply the exponential function on each and every point. If you're in doubt, print it out. Let's try it. np.exponential x values. Look at that. Okay? Those are all the exponential values. So the first entry is e to the -2. Correct? Because the first entry in the x values is -2. Agreed? Or in other words, x values at 0, the first entry is -2. Numpy dot exponential of x values is also going to be an array. Let's call them function values or fvals. That's an array as well. Okay. If I type fvals 0, I'm accessing only the first entry. That's 0.135. np.exp of -2 should be equal to also 0.135. You're in doubt, print it out, sanity checks, make sure you understand what's going on. Now, you agree that fvals is an array of values of the exponential function, each one corresponding to the values in the array x values. Agreed? Who disagrees? I like disagreement because it leads to thinking, right?
What if the disagreement is wrong?
Well, but it leads to a discussion, right? It's a learning opportunity, okay? Okay. All right, so we're going to come back here. Okay, now we're going to plot the function values versus the x values. Very simple. We're going to do PLT, which is the plotting library. The most basic plotting mechanism you're going to use is plt.plot. Now, what does plot take? Ooh, a bunch of args and whatever. It looks like a fancy, complicated signature. But if you scroll down, it shows you xy, plot xy. So the first argument is going to be the x values, and the second argument is going to be the y values. And if I execute this, ta-da, I get a plot of the exponential function. Okay?
How again did you bring up that data about the thing?
Pardon me?
Plot. You got all that information on plot. How did you do that again? Put your cursor over it, you press it?
No, so I press Shift Enter to execute a cell. Shift Enter.
But if you just, when you put your cursor over plot, to get the information.
Oh, the arguments is Shift Tab. Yeah, so you have to put the cursor inside the parentheses of the function and press Shift Tab. Okay? Shift Tab will give you a drop box with information about the function signature. Okay. Okay. This is great. Now we have a plot. But this plot is ugly because it's pixelated. So let me show you some magic. And I'm going to copy this magic because for the life of me, it's complicated to remember. But from now on, put it in every notebook where you're plotting. You see these two magic lines? They're actually called Python magic. These two things here. Matplotlib inline enforces that all plots are going to show up in your Jupyter notebook. More importantly here is going to tell, look, you're giving me beautiful, high quality visuals everywhere except for these darn plots. Why don't you make it a vector graphic? A vector graphic, if you've done graphics, is a graphic that is infinitely zoomable, like a font. You can zoom on it to infinity and you still see high quality graphics, right? So if you execute this, I'm going to run this again. Look at that. Okay, so now we can zoom this in. You can see all the plots. Everything is just looking nicer. Okay? Now you can clean up the plot a little bit. We'll work through that through the end of the class. We're going to add labels, right? So we can add labels. We can add a grid, etc. The most basic elements you want to add, let's just do it. plt.xLabel is to add a label. So I want to add a label to the x-axis. Just put x. And plt.ylabel, I'm going to put exponential or function values, whatever. Okay? Always label your axes. If you don't label them, I'm going to assume the x-axis is the number of alligators and the y-axis is the number of raspberries. All right? So if you don't label your plots in your homework, that's what I'm going to assume. I'm going to tell you, well, I didn't ask you to plot raspberries versus alligators, okay? Label your axes. It's not that hard, okay? One thing I like to add is a grid. It gives us a sense of direction. Okay, now that you know how to plot, now go ahead and do 1, 2, 3, and 4 terms in the Taylor series. Okay, I'm going to move the slides here. I don't know why this moved over here. Okay, let's move it to the right. Okay. So now that you know how to do the plotting, go ahead and plot E plus EX minus 1 plus E plus E times. So this is not exponential x minus 1. It's E times x minus 1, okay? Remember, we're trying to approximate the exponential function with the Taylor series. I'm going to see what happens if I take one term of the Taylor series, if I take 2 terms, 3 terms, 4 terms. 5 terms, etc. Each one of those is a function in and of itself. So go ahead, plot it on top of the full exponential function. Yes?
Correctly, when we plot this, is it just going to be a straight line at E?
The first function is going to be a constant. That's right. The second one is going to be a straight line. The third one is going to be a quadratic. But see what happens.
If x equals 0, or if x equals 1.
We're plotting over the, if x equal 1, see what happens.
Oh, plotting. Okay, so we're not plotting.
You need to plot it versus x. So remember, we're approximating the exponential around 1. But what happens as x changes away from 1? If you depart from 1, if you go to 1.5 or minus 1.5, right? What happens? Okay? All three plus there's, so I need up to 4 terms.
Does NP store the value of E somewhere?
Just do numpy.exp1.
Yeah.
So if you want to take a moment, if you're still kind of struggling with why we're doing this, let's frame it in another way. The Taylor series, if taken in full, is an exact representation of any continuous function. Okay? We know what the Taylor series looks like, first term, second term, third term, etc. And you can do the Taylor series around any neighborhood, any point. In this case, we chose the point a equal 1. And we approximated, or we wrote the Taylor series of e to the x near the point equal 1. Now I'm asking the question, what happens when I look at one term of the Taylor series, or 2 terms, or 3 terms, or 4 terms? Clearly, they're going to not be exact like the full exponential function, but they're going to be pretty darn good approximations, especially around the point 1, where we wrote the Taylor series. If we wrote the Taylor series around 2, those terms are going to be good in the vicinity of point 2. But what I want you to see is that, or what I want you to expect is, as you add more terms, you're going to get more and more accuracy even farther away from 1. That's the whole idea. If you've plotted, if you've done the plotting, raise your hand. Let me see, yeah. So did you see what I said? Is that your interpretation? Yeah.
I can see that.
Yeah. Okay. So let's see. The first function was, I'm going to just define those. And I'm going to say def f1 of x return np.exp of 1. So that's the first function. Def f2 of x. I wouldn't do it this way in practice, but since these are just 2, 3 functions, I'm just going to do it the brute force way. Okay, I'm going to return f1 of x plus, what is the second term? E times exponential times x minus 1 plus x minus 1 times np.exp of 1. Okay, and let's see. Define f3 of x, return f2 of x, right? Plus, what is the third term? 1 over 2 factorial x minus 1 squared times e. So 1, that's going to be 0.5. 0.5 times x minus 1 squared, squared times e. Okay? And then let's do f4. Those are 4 terms. Return f3 of x plus the fourth term is going to be 1 over 3 factorial, so 1 over 6 times x minus 1 cubed times np.exp 1. Okay? So now I'm going to plot those, okay, next to the exponential. The first one is going to be f1 at x values, right? So now, what is x? X values. X values. Okay. What I'm going to do here is the following. I know the error here. P dot ones. Okay.
What was that?
Okay, so the problem with matplotlib is, just do it this way now, and I'll explain it later. The problem with matplotlib is you need to plot a y array versus an x array. np.exp1 is a single value. So to turn it into an array, I multiplied it by another array of ones. Don't worry about that right now. We're going to cover this in a week. In 1 week, we're going to get there. But just see that the first value is just a constant, right? It's just a constant. And any point away from 1, it's very different from the true function. Agreed? So it's a terrible approximation. So let's see now if we add one more term. If we add one more term, so we're going to do the second function with 2 terms. And I'm going to do f2 of x values. Now, f2 is a straight line, but look at that. So compared to the full exponential, think of the blue line as the full Taylor series, okay, the true value, the true exponential function. With 1 term, we got the orange line. With 2 terms, we got a straight line. However, look, at 1, it's still very accurate, but also as we go away from 1, it's reasonably accurate compared to the blue line. But then as we are farther away from 1, the approximation deteriorates because we have only 2 terms in the Taylor series. With 3 terms, we should get better, right? So let's do 3 terms. F3. Now with 3 terms, we get this parabola, this red curve, and look at that. It's even closer to the blue line at points where the green line was bad. It's closer, but still, as you are far away from 1, which is the center of our approximation, right? We wrote the Taylor series around 1. That's the idea of the Taylor series, you know? In the neighborhood of 1, we have an approximation if we cut some of the terms out. Let's do one more function. Now this one is in purple. It's even better. Look over here. It covers more. It's closer to the blue line. But then it deteriorates, as expected. It's not going to be exactly equal to the exponential function because we only took a finite number of terms. Okay? This is just to visualize the Taylor series. The more terms you add, the better accuracy, but the more expensive the calculation is. Okay? All right, so I'm going to switch back to the slides. So like I said, in practice, we cannot add an infinite number of terms, and hence we have to truncate this infinite series. Now, the term at which you truncate defines both your approximation and your truncation error, because the terms that you neglected are, by definition, your truncation error, right? So if you were to truncate, let's say, at that term, n over there, then this defines your approximation, and this defines your truncation error. We know what it is. Okay, we know what the truncation error is in this case, especially if you know what the function f is. Okay, so we know the truncation error. In general, if you truncate at term n, the truncation error will be exactly a truncation. It's still an infinite series, but it starts with 1 over n factorial, n's derivative at a of f at a times x minus a to the power n, and so on, an infinite number of terms. So that's not very exciting, because if you want to estimate the truncation error, you still have an infinite number of terms to calculate. Okay? Luckily, the truncation error can be written in a very concise form. All of this infinite series, can be collapsed into this first term evaluated at a special value we call xi. And that value is somewhere between x and x plus a, and x minus a, x plus a, or x minus a. Let me fix this. Give me a minute here. X plus a. Okay, between x and a is between x and x plus a. Okay. So now the truncation error can be expressed as a single term with the nth derivative evaluated at some value between x and x plus a. In practice, we don't know what that value is. But what's important here is that this value is bounded. It doesn't go to infinity. It doesn't go to 0. It's some fixed finite value. What that means is that your truncation error is only controlled by the distance between x and a. We learn that when we get to finite differences. We're going to learn that. We're going to spend more time on this. But I'm just exposing you to the idea of this truncation error. Okay? We'll leave it at that. Now, another way the Taylor series can be written is, rather than saying, okay, I'm expanding in the neighborhood of a fixed point A, no, I'm going to pick an arbitrary point x, and I want the Taylor series in the vicinity of this arbitrary point x. It's exactly the same, but it changes the equation just a little bit. It makes it more useful for engineering analysis. And this is written as, at an arbitrary point x, could be any point. Could be 1, could be 5, could be 17. At an arbitrary point x in space, the function evaluated at x plus h, where h is in the vicinity of x, just like a, we fixed a, then that function at x plus h is equal to the function at x plus h times its derivative plus h squared over 2 times second derivative, and so on. It's the same formula. It's just written in a different way. This is going to be more useful for engineering analysis. Okay? It holds the same meaning as before, that any continuous function can be expressed as a polynomial in the vicinity, not in. Like I'm typing it and I'm stressing the in, so I end up typing I double n. Fix that. Okay. Now this form is going to be very useful when we build what's called finite difference approximations to derivatives. This single equation is the foundation of everything I do in my research. Solving ordinary differential equations and partial differential equations, doing fluid flow simulations, this single equation up there is the foundation of all of that analysis. Okay? So let's see you put it to practice. What I want you to do is take this f of x plus h, this formula, this is standard formula for any f, and I want you to use that formula to derive the forward Euler approximation to the first derivative. Now look at the terms. So derive it from this formula and show me the truncation error. In school, in high school, you learned that this is the definition of a derivative, rise over run in the limit as h goes to 0. Now I'm taking this up a notch, showing you that this comes from the Taylor series. So now if h is not 0, you have a truncation error. Okay, so derive that from this single equation. Get me a formula for f prime. Get me this formula for f prime and show me the truncation error. No, for any function. For any function f. Get this one, and whatever is left is your truncation error, right?
Oh, so.
Yeah, just write the first few terms of the truncation error. Take that equation up there and solve for f prime.
So our truncation error would be.
But then truncate. Well, that's the idea. We're doing numerical analysis here.
Where do we truncate at?
You truncate after this, okay? So suppose you know the function values. Sorry to interrupt you, but suppose you know the function values at x plus h and x. That's all you know. And you want an estimate for the first derivative. And you truncate everything you don't know. Numerical analysis. You can write it down. Just start writing down. Yeah, you have to start thinking in terms of actually doing something. Just write it down. This is a numerical approximation. Okay? Suppose you know the function values at x plus h and x. Or just suppose you know the function only. You know f. Wow. Right?
Oh my god.
You solved it. Okay.
I got that.
So now write down the truncation error.
So we're not assuming the limit to 0, right?
This is an arbitrary function. Uh-huh. It's one line. It's one line. Don't overcomplicate it. You have an exact equation up there. Okay, let me reframe it in another way. Suppose I only know information about the function, and I know how to evaluate it anywhere in the world. I only know f. So I can evaluate f at x plus h and f at x. X is any value. So for example, I can evaluate it at f of 1 plus 0.3 and f at 1, right? I know the function, but I don't know anything about its derivatives. And I'm asking you to use that first formula to get me an approximation for the derivative, and I'm giving you this approximation. Use that formula to derive this and neglect everything else. Everything else that you've neglected is your truncation error. Write it down, draw a line, and say this is truncation and this is approximation. Solve for f prime, guys. Just solve for f prime. If this is hard for you, it's going to get harder, okay? It's going to get way harder. Okay. This is an exact formula, all right? This is an exact formula. I'm looking, all I know is f. All I know is f. I can evaluate f anywhere I want. And I want an estimate for f prime at any point x. Okay, I don't know f double prime, f triple prime, and I'm not going to really care about those. So from this equation, I want to extract a formula for f prime. Okay, here's what I'm going to do. I'm going to isolate f prime. So move everything to one side, or put hf prime on the left, everything on the right. So we get a formula. This is still exact. This is still, I didn't do anything here. Next, divide by h. Right? I'm going to divide by h. Okay? Did I do anything out of the ordinary here? No, nothing.
So it's just algebra.
It's just algebra, exactly, it's just algebra. You guys are overcomplicating this.
I'm not that smart.
Well, now in your high school you say, in the limit as h approaches 0, what happens as h approaches 0? All of those terms actually disappear because these functions are bounded, right? So they're finite values. You multiply them by 0, they disappear, and you get the approximation for the derivative. But what if h is not 0? Then those terms are not 0, and that's a truncation error. So if you were to truncate over here. That's your approximation. That's the forward Euler approximation, the rise over run. And this is your actual error that you're committing in doing this approximation. So if you knew the true value of the function, and you approximate the true value of the derivative, you approximate it with this, then this is the error you're committing. Now, if you notice if you remember, one second. If you remember the shorthand of the truncation error, all of this infinite series, someone said it's infinite. Yeah, it's infinite, but it's also bounded by this. This entire truncation error is equal exactly to 1 over 2 times h, which is the distance from x, times f double prime at some value c. And I said that this f double prime is bounded, so it's finite. It's a finite value. It's not infinite, doesn't change with x. It's just a finite fixed value. So what matters here is h. The smaller the h is, the smaller the truncation error. That's what we expect, right? Okay. So that's the question now. Again, consider this approximation. As we're shrinking h to go to 0, that's what you learned. That's what makes sense in your mind, right? That this definition of the derivative is exact and the limit as h approaches 0. But now I have a formula for the truncation error, right? So what do you expect as h approaches 0? What's going to happen to the error? Okay, who says it's going to go to 0? Okay. I say the truncation error is going to go to 0. Who says it's not going to go to 0? I also say it's not going to go to 0. What happens to the truncation error as you shrink h? Gets smaller, right? Because it is proportional. This f double prime is bounded, and h is just proportional to h. As h goes to 0, the truncation error goes to 0. Yes?
What is that squiggly line?
It's called xi, xi. So it's a Greek symbol. It's just a value between x and x plus h. Some value. Okay? Connor.
So if we can find the truncation error like this, why do we have this approximation? Why don't we have the approximation?
Because we don't know what the function is. Because this method we're going to use to actually approximate the function itself in the future. So in the future, we're going to not be dealing with functions. We're going to be dealing with differential equations or derivatives of the functions. So we don't know what the functions are. So we're going to use this method to find the function itself. We'll get to there. Great points. And I know some of these things don't make sense. And it's hard. It's one of those things where you gotta, I don't want you to just trust me on this. I'm trying to rationalize as much as possible. But some items, you gotta just accept them and just bear with me until we get to the point where you're gonna get this eureka moment, okay? So now let's get back to this. Just bear with me. As h goes to 0, we expect that this approximation to become exact, correct? As we learned in high school. And indeed, the truncation error shows that. And most of you said, yes, the truncation error goes to 0. So if we were to go ahead and take an actual function where we know is the derivative, exactly. No approximations in that derivative, even. We know exactly the true value of the derivative. And if we were to compute an approximation to the derivative with this formula and keep shrinking h, we're going to expect for the error, the true error, to go down to 0. Agreed? So if we were to plot the true error between some function and its approximation versus h, as h goes to 0, we're going to see that error decrease. Agreed? Okay, let's see what happens. Take the function x squared plus 3 minus 3x plus 1. There's a reason why I chose a polynomial, because you can evaluate it exactly, the derivative. No approximation, the derivative, okay? Even on the calculator. Compute the first derivative approximation using this forward Euler approximation at x equals 0.5, okay? and then just change h from 0.1, 10 minus 2, 10 minus 4, 10 minus 12. That's pretty darn small, right? So we're pushing h to go to 0. And then report the error between the exact derivative and the approximate derivative and plot it. If our discussion is correct, then we should see the error go to 0 as h approaches 0. Agreed? Okay. So again, we're trying to prove that the truncation error, or the error, that's the only error we've committed, right? In this derivative approximation. It's a truncation error, and it's only proportional to h. So as h goes to 0, the error should go to 0. Try this out for this function, x squared minus 3x plus 1. The derivative for this is 2x minus 3, and evaluate that at 0.5. That gives you the exact value of the derivative at 0.5. Now compare, start calculating the derivative at those h values. Okay? Working groups are going to be floating around. So it would help if you define h as a numpy array. So put those brackets as a numpy array, okay, and then compute the derivative in one shot. Okay, you have the function f. You know the exact derivative value. Take the difference. We did this. We did something similar early on. I'm here to help. Raise your hand.
Is there a function for like something to write 10 to the negative 2?
1e minus 12. Just so put 1e minus 2. Yep. 1e minus. I would put actually 1.0. Yeah, 1.0 to make sure that. All good over here in the back? I rarely come here. It's pretty chilly over here.
I have some issues with his imports.
Yeah, so you gotta install NumPy.
Would you mind teaching me?
You have to figure it out. I mean, this should come with the distribution. So whatever you installed last time, Anaconda, or I don't remember what we did. So you could open up the terminal and create a new. So weren't you following us last week where we did NumPy stuff? So it was working and now it's not working? But last week it was working?
Yeah, it works.
Okay, this should work. But so if any of those issues show up, like, let's get to them sooner. Okay? All right. If it's not working, work with your colleague. Notebook's not working. Jump on the CHPC one, maybe. Or work with Brooklyn. Okay, how we doing? Did you get something? No? No, not yet. Okay. I'm not looking at your screens. I'm just walking by. Don't feel like we're making a mistake and nervous. I know if someone is looking at me, I'm typing, I make a ton of mistakes, so I'm not looking. What about you, TAs? You're not working. Oh, you're the TAs. You already know the answer. Anyone got something? Anyone got a plot? Were you stuck? Put your names out, or I'm going to call you anonymous. Yep, perfect. You're on the right track. No, you're going to compare now the true value with the approximate value, right? We're not comparing. We're not doing Taylor series. Yeah.
Just with the steps to take, according to f of x, can I use that to plug into that formula?
Correct, correct. And you need an exact value for the derivative as well. And here you don't have to do to the power. You do 1e minus 2. Just 1.0 e minus 2, 1.0. This is a more expensive calculation.
Okay.
This will actually do a power.
Okay, so then after this, should I put these values into an array, or what do I do? Like, what's the next step I should take? So you said a derivative.
So you need a derivative function as well, right? And you need whatever you want to call it, like df, and it's going to take in, like we did something similar last week. So open up that notebook and try to kind of replicate some of the items. Yep. So this is all just exactly like this, okay? But then you want to compare the true value with the approximate value.
And true value is the first one, and the approximate value. The true value is just the regular.
Yeah, exactly. The true value is the exact derivative, okay? Yeah.
Did you mean for the first one to be 0.1? Because isn't 10 to the negative 2 also just 0.1?
No. It's 0.01. Okay. 1e to the minus 2. So we'll put 1e to the minus 2. That's so. All right. Anything working, Miles?
Okay, what am I doing wrong?
So
I created an NP array of the values of h. I set the Rx value. I set the original function. In the
So this is not an error. This is a derivative, right? Yeah. So the error is going to be b minus a.
I didn't do a return.
Yeah, you didn't do a return. Yeah. 1 second. Yes. Yeah, you have to restart the notebook. Come to the help session, okay, and Brooke and Nicholas will be able to help you. Yeah, you had a question, sorry.
Is there a matplot function for a log-log scale, like how you want
plt.loglog.
log-log? Because I know
Yeah.
that's semi-log. I just didn't
Yeah, yeah, you could do just log. Yeah. All right, almost there. Got 2 questions here. Let's see.
So what does this error mean? So I know these work. I'm guessing it's similar to how I've done.
Yeah, so this is wrong. You can't put it in parentheses. You have to put them in square brackets and put it in a NumPy array. Okay?
Oh, that's okay.
Yeah.
So NP dot array.
Yep, and p.array, and then open parentheses. All right, let's see. Did you figure it out? Oh, here was the question. Okay. So
I just don't know how to take out the line. I forgot how to.
can you do it on a log plot? So plt.loglog.
Yeah, I just Did I do it in the wrong order? Should I do h then error? Should I do h as the x?
So you're plotting the error versus, yeah, so error on the y-axis. Error on the y-axis. Okay. I'm gonna solve it. It's not right.
But I have to label my axis.
Okay, so label your axis. Yep, you're gonna plot error versus h, okay? Error versus the spacing. The error is between the true and the approximation. Okay. I'll give you, what was going on? Yes. Yes. So what does this say?
I thought it would keep decreasing. But
Yeah. Yeah. Think about why. Good work, Josh. Okay. So let's try to do this together.
oh, there we go. No, still not right.
Okay. So far we got only one plot right. So I think the programming is kind of standing in the way. So let's do the programming together. And also, I'm going to go ahead and import the same kind of boilerplate over here. Whoops. New notebook. Okay. Let's see. So we were expecting that the error when comparing the, so if we take the exact value of the derivative and subtract from it the forward Euler difference, only fx plus h minus f of x over h, that difference is going to be the truncation error. That's the definition of the truncation error, right? Then we asked, okay, we expect the truncation error to go to 0 as h goes to 0. So if we were to plot the error between the exact derivative and the approximate derivative versus h, that error is going to go to 0 as h is decreasing. Okay? Let's see what happens. We imported the boilerplate stuff. First, I'm going to define my function. Let's say, of x, and I'm going to return, what was it, was x squared minus 3x plus 1. Now I'm going to define the derivative. Okay, so let's say define the function whose derivative we wish to approximate. Now, define the forward difference or forward Euler derivative approximation. So we did this last week, right? df. And I'm going to give this an arbitrary function, a value x, and the spacing h. And we're going to return f at x plus h, minus f at x over h. That's the definition of the forward difference. Okay? Now, the true value of the derivative, so x is 0.5, and the true value is equal, what is the derivative of x squared minus 3x plus 1? It's 2x, right, minus 3.0. Agreed? So now, this will automatically pick up this value of x and give us a true value for the derivative. Now, what is the error? Is the difference between the true value minus this. That's our error. And it's a true error. So, and we did this also last week, just to remind you, if we were to say h equals 0.1, and then do df of my function at x and h minus the true value, and put them in absolute value, that gives me an error. Okay, that's an error. Okay. However, we're going to do it for different values of h. And we're going to do h is equal 0.1, 1.0 e to the minus 2. So that will give us all the rest of the values. And so 1.0 e to the minus 4, and 1.0 e to the minus 6, 1.0 e to the minus 8, and then 1.0 e to the minus 10, and 1.0 e to the minus 12. I'm going to make this a NumPy array. Okay. So now the error, or true error, is the absolute value of the true value minus the numerical derivative, or the forward Euler method, the forward Euler approximation, which is my function at x and all the h values. Okay, so now true error is actually an array. True error, right? It's an array. I don't want to show you the values yet because I want to see the plot. Now, the next step, best thing is to visualize. I want to plot this error versus h, okay, on a log-log plot. So I'm going to do plt.log-log, and I want, in the x-axis, I want the h values, and on the y-axis, I want the true error, okay? And I'm going to add something here. I'll explain it in a minute. I want to add a circle at every point we're computing the error, at every h value, and I'm going to connect them with a line, okay? But I also want to do a couple of other things. And you didn't have to do that, but because we tend to kind of want to associate a decreasing error with decreasing values of h, I want the x-axis to be, rather than go from 0 to infinity, I want it to go from infinity to 0. I want it to be in reverse order. So, okay. So if we were to plot this, this is what we would get. Now, when you look at the x-axis, h is decreasing this way, okay? And this is the error. So if we start at h equal 0.1 and 0.01, okay, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, the error is decreasing. Then something happens here. The error starts increasing. What the heck is going on? If you still trust computers and numerical methods, then you should stop. Because there's more to this madness than meets the eye, like Optimus Prime. You know? There's more than meets the eye. The error is decreasing. And then something happens at some value of h, in this case just happens to be 10 to the minus 8, and then the error starts increasing again. Look at that, it's significant, 10 to the minus 4. It's almost the same as this error over here. It's pretty high, significant error. So there goes out of the door your high school definition of the derivative, that as h approaches 0, the error should go to 0. It doesn't.
Oh, wait, actually? So the computer's not just being weird, this is actually the correct graph? Does it?
This is a correct graph on a computer. This is what all of you should be getting this plot. Are you?
Well, I am now.
Yeah?
I didn't know there was this plot logarithmically.
Connor.
So, to be clear, does this not have anything to do with the truncation error of the computer?
What is that called? So we define roundoff error. Okay.
This isn't roundoff error?
Is it?
I don't know.
It's a good point. Okay, so now who revises their claim? Who takes their hand? So I raised my hand for both. I said, yes, the truncation error should go to 0, but also the error is not going to go to 0. And notice how I played on words. I said truncation error, and then I said error. The truncation error does go to 0. But we forgot about another error. We forgot about the roundoff error. In our evaluation, in this evaluation here, there is roundoff error when you evaluate fx plus h minus f of x. Roundoff error in the numerator divided by h. As h goes to 0, roundoff is going to amplify. So now you have two components of the error. What we wrote on the board is not numerically exact. When we wrote on the slides, was analytically correct.
But you said the graph is correct.
The graph is correct. So you see here, what's happening here, roundoff error is dominating. So truncation error keeps going to 0, but roundoff error starts dominating as h gets smaller and smaller. The graph is correct. Because what you're looking at here is actually what I'm going to call as the total error. The total error. Every time you're on a computer, you have roundoff errors And most of the time, you're going to have truncation because you're approximating exact formulas. In this case, yeah, the truncation error, I stand by this argument. Yes, it's going to go to 0 because the truncation error is proportional to h. As h goes to 0, the truncation error goes to 0. But the round-off error is not going to go to 0 because it's divided by h. It's going to amplify. It's going to get bigger and bigger. Okay? And this happens for these finite difference approximations. So this is a nightmare in all problems of computational fluid dynamics, computational heat transfer, computational solid mechanics, because they're all based on this approximation, fx plus h minus f of x over h and its variance. Round-off error is going to dominate. So we cannot just blindly say, oh, we're going to increase our resolution and put more points in our calculation to gain more accuracy. No. There's a point beyond which you're not going to gain any more accuracy. You're going to be limited by your computer. The formula on the slides here, this formula assumes that this guy is computed with infinite precision. Once you put it on a computer, you have to add plus round-off error. And then divided by h. Round-off error is generally fixed. Divide by h. As h is shrinking, you have two competing effects. Truncation error is going to 0. Round-off error is going up. In your homework, you're going to derive an ideal h value where round-off error and truncation error are just equal. And that's the best point. Yeah. 3. Yeah. No, you didn't see. I was going to teach. I wanted it to be on homework too. OK. Let's take 3 minutes.